Yeah, welcome everyone. Welcome to the Spring 2026 GSC seminar series. Today is March 11th, 2026. Uh, Before moving to our presentation for today, let's take a look at the GSC leadership team for the academic year 2025-26. We have Rodney, Hurt, and Samuel as our co-chairs. Uh, Publicity is handled by Swapnil, Hafiz, and myself. We have Siavash and Anshu working as our co-treasurers, and we have a large support team of Zareen, Roshan, Rachel, Suramya, Vibha, and Nurayan. And we all work under the wonderful mentorship of our mentor, Dr. Farooq Mistry. So GSC has regular meetings on Wednesdays at 6 p.m. on Zoom. So if you want to be a part of these meetings, please do join the leadership team. The time is set as per the schedule of all attending members at the start of the semester. So if you want to join, please email Rodney or Samuel. We also have a engage page, which helps us keep attendance of our events and helps us secure funding. So if you are affiliated with OU, just use your OU ID to join us on our engage page. You can just scan this QR code. We also have our LinkedIn page where we are continuing to grow our community and help connect people over the LinkedIn. So do check out our LinkedIn page if you want to connect our past or future speakers. Do take a look at our page. So we do have a Facebook and Instagram page where we do the promotions of our events uh, like ASME Lightning Talks or International Food Festival and the webinars. So all of the promotions are on those pages. So do check those out. So we have a YouTube page where we keep all of our past recorded webinars. So if you're interested in any particular topic or a speaker which you couldn't attend, you can go to the GSC-GCOE OU YouTube page and listen to the recorded webinars. For the leadership team, we have a Dave and Susan Bird team room with all the basic amenities for students to just relax, hang out, or have a study room if they don't have a space of their own. So if you would like an access to this room, do become a member of the GSC and just provide us with your OU ID and we will get you the access. Just a reminder, we will be putting in the chat Google form for recording the attendance of this webinar. This helps us in getting or securing the funds to get lunches for this webinar. So please do fill these forms. So this seminar series, we are exploring the research frontiers with generative AI, looking at the issues, methods, and applications. We know how AI is reshaping research industry and society, but how do we do it responsibly is the big question. And through this webinar series, the speakers are exploring these topics. So our forthcoming webinars are on March 26th. We have Dr. Morshed Khandekar, who is a professor at the School of Engineering at University of Central Oklahoma. Then on April 2nd, we have Suramya Sarkar, who is a Ph.D. student in the School of Aerospace and Systems Engineering, or sorry, is in the School of Industrial and Systems Engineering. She's also a part of the GSC leadership team. And on April 8th, we have Parinas Dastur, who will be presenting on machine learning framework for early lung cancer screening. So do check out those webinars as well. So today we have Vishnu Kadiyala, who is a PhD candidate in the School of Computer Science at OU. He's working with Dr. Mohammad Atiquzaman. He will be presenting on latent belief driven multi-agent coordination. A little bit about Vishnu. Uh, I've been friends with him for a long time now at OU. He has done his master's at OU in the School of Electrical and Computer Engineering. Uh, he had worked on the GeoCarb laboratory and with Dr. Andy Fag on data-driven mod or deep learning models for weather data. And like us, he's a big cricket enthusiast. So without further ado, Vishnu, the floor is yours.
Thank you, Avinash, for the great introduction. Uh, okay. Okay. Good afternoon, everyone. Thank you for being here. Before I start, I want you to picture this. So there are like two human drivers that arrive at an unsignalized intersection at the same time. There are no traffic lights. There's no stop sign telling who goes first. So what do? You watch, right? You glance at the other driver, read their speed, maybe catch a subtle gesture. Are they slowing down? Are they pushing through? In a split second, you make a judgment call. You either go or you yield. No words are exchanged. There's no protocol. You just observe and you infer. Now, imagine replacing these human drivers with autonomous vehicles. Two self-driving cars approaching the same uncontrolled intersection. They can perceive each other through sensors, but there's no centralized system coordinating them. How do they learn to negotiate that intersection? The way we do, just by watching. So that's the question at the heart of today's talk. My name is Vishnu Kadiyala. I'm a PhD candidate here at University of Oklahoma, and today I'll present VABL, Variational Attention-Based Belief Learning. This is a framework for decentralized agents that learn to coordinate implicitly by building mental models of their teammates from observations alone. So here's the roadmap. I'll start by motivating why implicit coordination matters. Then I'll give you some background on decentralized multi-agent reinforcement learning. After that, I'll introduce the VABL framework, the three key ideas behind it, and walk through the architecture. Then we'll look at our experiment results on overcooked AI and other benchmarks and do a deep dive into ablations and stability analysis. And then we'll finish up with some future direction, including the application to autonomous driving. And at the end, I'll keep about 15 minutes for questions. So why should we care about implicit coordination in the first place, right? Think about teams that coordinate in real world. You can think of autonomous vehicles that are navigating an intersection. They need to negotiate who goes first without a central traffic controller. Or maybe robots in a warehouse. One robot is carrying like a huge box towards a shelf, and another needs to clear the path, but they cannot communicate with each other. Or maybe it's the emergency response team in a disaster zone. The communications are down, but somehow the team still needs to divide tasks and work together. Or maybe it's a kitchen staff during a dinner rush. The chef and sous chef are working in a cramped space, anticipating each other's movements to get the orders out on time. So, what do all of these have in common? Whether it's human or it's artificial, uh, they're operating under partial observability. So, what it means is each one sees only their little corner of the world. There's no shared global picture. Communication is either limited or it's non existent. And yet, somehow, they have to coordinate. So, here's the key insight that drives our work. In psychology, there's a concept called theory of mind, the ability to attribute mental states of others. So it could be their beliefs, their desires, their intentions. So how do you model these things? right? So a simple example is when you're driving and you see another car inching forward at an intersection, you infer that they're about to go, right? You don't communicate, you just observe and then you predict. The question we are asking is, can we give the same ability to AI agents? Can they learn to infer what their teammates intend to do just by watching their actions? So that's where VABL comes in. Uh, Let me set up the stage with some background on how multi-agent reinforcement learning typically works. So uh, the standard paradigm is called CTD. It's centralized training, decentralized execution. During training, you have access to the full global state. So what this means is that all the agents are able to look at each other's actions. They're able to look at what every other agent is doing. And this is during the training phase. But at execution time, each agent only has its own local observation. So during the execution, it can only rely on what it can see, right? So you train with full information and then you deploy with partial information. So this is the standard setup that we all use for cooperative multi-agent reinforcement learning. So now looking at the existing approaches. So these existing approaches fall in a few camps. First, there's MAPO, multi-agent PPO. This uses independent actors, each making their own decisions with shared centralized critic during training. So there's like one central critic that's um, looking over all the agents. So MAPO is currently it is one of the strongest methods on many benchmarks. It is powerful, but as we'll see, it can be fragile. Agents can learn good coordination early in training, but then lose it. The second approach is QMix. So in QMix, what we do is we take the value decomposition approach. So each agent has its own value function, and there's a mixing network that takes all of these values from all of these agents, and it builds a joint value. So more like averaging on everyone's value. A value is something like you can think of it as um, an agent that's sorry. Uh, a value is something like you can think of it like what the agent is focused on, right? And the third, there are communication-based methods like ComNet and Tarmac, where agents explicitly send messages to each other through learned communication channel. These work, but they require communication bandwidth, which isn't always available, right? So here is where the gap comes in. So the current methods, they either ignore teammate modeling entirely, just like MAPO and QMix. They don't try to understand what their teammates are thinking, right? Or they require explicit communication channels. So none of these methods actually learn how to infer intent from observation. This is the space VABL fills in. So let me introduce VABL, the framework like variational attention-based belief learning. So this framework, it relies on these three pillars. So pillar number one is attention-based interaction modeling. So we use cross-attention mechanism or teammates' observable actions. This lets each agent build a rich context vector that captures what its teammates are doing with a focus on teammates that matter the most. So what this essentially means is that uh, the attention mechanism here is looking at all the actions that all of these teammates are doing, and it will fix on which is more important for me. So the attention-based interaction modeling is taking only the relevant information that it needs and building rich context vectors out of it. The second pillar is latent belief representation. So this is a belief state that the um, the agent holds. So over time, this belief is getting updated with new information. So for example, it has a new observation and there are like other actions these agents are performing. So it looks at all of that and it updates the belief. So for example, there are like three agents and you see that agent number one is more cooperative than agent number two. So this is a belief that gets updated into our agent as time passes, depending on the actions that these agents are performing. So that is the second pillar. And the third pillar, theory of mind auxiliary objective, we add a predictor head. It tries to predict what teammates will do next. So why do we need to predict this, right? So why we do this is it forces the belief state to contain useful information. So if you are able to predict others' information based on the local observations that we have, then what is happening is your attention-based interaction modeling is capturing only the useful information from the local observation. Together, these three components enable agents to anticipate collaborative strategies and adapt their own behavior accordingly. And all of this is happening without any explicit communication. So let me walk you through the architecture so you can see how these pieces fit together. So the data here flows from left to right, and there are two input streams. One of them is observation encoder on the top left here, and there's action encoder on the bottom left. So the observation encoder, what it does is it looks at the present observation or what the agent can see, and it is going to convert that into an embedding vector. So these embedding vectors are then passed on to our attention module. The cross attention module is the attention module here. And the action encoder, what it does is it takes previous actions of these teammates and it encodes each one of them into an embedding vector and it passes that to the attention mode. So the significance of this is that the observation encoder will encode the current observation, like what I'm able to see at this present moment. And the action encoder looks at all the previous actions my teammates have taken. So for example, in the observation encoder, I see that there are like 3 teammates that I'm working with right now. And in the action encoder says that these 3 teammates have been doing so and so actions in the previous observations. So we take both of these information and we combine them using the cross attention module. So the agent's current belief state from the previous time step is taken as the query here in the attention module, and the encoded teammates action become keys and values. The attention weight computed as a softmax of the scale dot product. This is more of the mathematics of how the cross attention module is working. So based on this, what happens is at the end you get what teammates' actions are most informative. We also apply a visibility mask here. Because in partially observable settings, not every time you can see all the agents. For example, if you're looking forward, there are like 2 agents in front of you and there's 1 agent behind you. So with partial observability, what it means is that the two agents that are in front of you are visible to you, but the one that's behind you is not. So that is what visibility mask does here. It like removes the agents that are not visible in the current observation. So the attention output from here, context-rich vector, is then passed for GRU belief update. So this is the internal belief state that our agent is carrying. So the inputs here are the concatenated observation and a rich context vector that we have, and also the previous belief that the agent had. So we have 2 outputs from this belief. So one is policy head and the other is auxiliary predictor. So the policy head decides what action our agent has to take. So it is more about telling, like, based on what I see and what other agents are doing, this is what action I have to take. That is what is decided by the policy head. And the auxiliary predictor is predicting teammates' next action. So as we discussed earlier, like this helps us, the auxiliary predictor helps the cross attention module to get only the useful information. So one more important piece here is the centralized critic. So during training, there is a centralized critic. It is a separate multi-layer perceptron that takes full global state and outputs a value estimation. So a centralized critic, it's used only during training. but it is not used during deployment. And the training objective, it combines these, like we maximize the PPO objective minus lambda times the auxiliary predictive loss, right? The PPO objective is the standard like reinforcement learning objective, and we added on the lambda auxiliary loss to it. So let's look at the training objective more closely, right? The equation is very straightforward. It's just maximizing the j theta minus lambda L ox. So on the left side, the j theta is this is the standard PPO, and we use the standard ranges for that. That's being used in Mapo. So all of these variables or the hyperparameters match that of Mapo's implementation, so that we have an apples to apples comparison with Mapo. And then we have the teammate action prediction. So this prediction is a cross entropy loss. So we are predicting which action each teammate will take next using only the agent's current belief state. This idea comes from like the theory of mind literature. If your mental model of the teammate is good, then you should be able to predict what they're going to do next. So the key hyperparameter here is lambda. So we have set the lambda to 0.05. This balances both the task performance with belief quality. If the lambda is too small, then the auxiliary loss has no impact on the training objective, meaning the like technically whatever we are predicting here will not be used for updating our model's belief. But if the lambda is too high, then the auxiliary task will like take over the whole training objective. So it will only learn to predict the next action of the teammate rather than predicting or rather than building more collaborative approach or coordination tasks. So let me zoom into the attention mechanism here, right? Because that is the most important part of our whole architecture. So the query is derived from agent's current belief. The keys and values are from the encoded actions. The attention weights are again like a computed softmax of these values and times visibility. So what does this buy us, right? Why are we doing this? So first, it's scalable. So for example, what it means is it works with variable number of agents. You can work with like 3 agents, you can work with 5 agents, or you can even work with 10 agents. So it is scalable to different number of agents at different times. Second, it's selective. So not all teammates are equally relevant at any given moment, right? So for example, you're working in a kitchen and there's like one chef that's working in the other corner of the room who is cutting some vegetables, and there is someone else who is handing over a plate to you. So who do you focus more on, right? You focus more on the person who's handing the plate to you because that's something that needs your attention for collaborative task. So that is what the attention helps us achieve. And it is differentiable. The entire mechanism is end-to-end trainable with PPO. So there's no hard routing or discrete attention. It's smooth and gradient friendly, and it needs to be differentiable for any machine learning method for it to work on GPUs. Fourth, it's visibility aware, as in partially observable environments, as I explained earlier, you can't see all teammates. The visibility mask ensures that the model doesn't attend to information that wouldn't be available when it's actually deployed on the ground. So thinking back to the intersection example from the beginning, the attention mechanism is like the driver who is checking surroundings. So who's selecting and focusing on what to focus on. Like you see a vehicle that stopped. Is it inching forward? That is something that you're looking at. So that is the task that attention here is performing for us. So let me briefly describe our experimental setup. So we evaluate on 3 environments. So the primary environment that we have is overcooked AI with asymmetric advantages layout. So this is a complex kitchen coordination task where 2 agents have to cooperate to prepare and serve dishes. But the interesting thing is both the agents do not have all the equipment. So one of them has ingredients, the other one has the tools to cook. So they have to coordinate on what each of what the other chef needs. So here the agent will perform all the perform actions which gives all the ingredients to the other chef, and the other chef will prepare and send out the dishes. So this is a very interesting task because it requires a high level of coordination. Uh, so in which the agents need to figure out who does what and without being told. So like throughout this whole experiment phase, do remember that we have no explicit communication. That means you cannot tell the other agent what you want from them. So this is all based on inferring just by looking or observing. So the second test is, or the second experimental setup we have is overcooked AI cramped room layout. So this emphasizes on collision avoidance in tight spaces, meaning like the motion of all of these agents, they have to make sure that they're not bumping into each other. They have to make sure that they leave space for other agents. At the same time, they also complete their own tasks. And the third is a custom, like simple coordination environment. It serves as a quick validation test bed. So our baselines here are Mapo, QMix. So Mapo and QMix both are well established in the reinforcement learning literature. So Mapo is the current go-to for policy gradient methods, and QMix represents the value decomposition approach. So the key hyperparameters, the lambda PPO epochs. Um, so PPO epochs, we set it to 10. That's the standard that they used in the MAPO paper. So what it means is for every 10 epochs, the PPO gets updated. It's a policy that trains the reinforcement learning model that gets updated. And the clip parameter here, 0.2, is that like, let's say uh, you want to move an object 10 centimeters. What this forces it to do is it moves it only 20% of that. So it moves only 2 centimeters instead of moving it 10 centimeters. What it helps us do is it makes it more stable in the sense that each action doesn't like push the model to make very large predictions. So we are sort of regularizing the model to make more judged predictions here. Yeah. So let's look at the results now, starting with overcooked. On the left, you can see that the learning curves over training. On the right, there are a few key numbers that I've pulled out from that. So VABL achieves a final reward of 28.1. So what about MAPO? MAPO just 8.6. So that's 3.3 times higher. So VABL is achieving like a 3.3 times higher final reward than that of MAPO. But here is where it gets interesting, right? So if you look at MAPO's curves over here, initially it looks like it reaches a pretty good peak, about 35.5, and that's competitive. But then watch what happens. Like it goes ahead and collapses. By the end of training, it's down to 8.6. That's like a 76% drop from its peak. VABL also has some drop off. Our peak is 45.6 and we end up at 28.1. But that's only like a 38% collapse as compared to MAPO's 76% drop. So in essence, we keep most of our gains. Then there's QMix. It appears to be very stable, but it never learns to coordinate. So what this tells us is that VABL isn't just reaching higher performance, it's maintaining it. Mapo finds a good coordination early, but cannot hold on to it. But VABL, it can. So let's see if this holds up on a different environment. On a simple coordination task, VABL achieves 103.1 as its final reward, which is 17% higher than Mapo's 88.0. But look at the variance here. This is what really stands out. VABL standard deviation is 1.7 and MAPOS is 20.3. That's like an order of magnitude more consistent. QMix completely fails on this environment with a negative reward of minus 5.5. So the problem with QMix here is that it's not able to learn coordination. So what this also helps us see is how coordination heavy these tasks are. So these results are across two very different environments, and they confirm that VABL's advantages are robust, both the performance improvement and the consistency improvement. Let me sort of dig deeper into the stability story here, because I think it's our most important contribution. We defined collapse as the percentage drop from the best reward achieved during the training to the final reward. So a higher collapse rate means that the algorithm found good coordination but couldn't maintain it. This figure shows the phenomenon from two angles. On the left side, the learning curves with the collapse points marked, right? So the collapse points are marked on this figure. You can see exactly where the MAPO starts to degrade. So here is where the MAPO starts to degrade. Uh, in the middle, like you can see, this is so the solid bar here is the highest reward it is able to achieve, and the strike bar here is the final reward it ended up with. So the difference between this is the collapse, like how big of a collapse there is. So for MAPO, the best reward is around 45, but the final reward is just under 10. That's like a 76% collapse. But for VABL, it's much better. The gap is better, where there's just like a 36% collapse. So you can ignore the rightmost panel here. It shows collapse rate across seeds. Since all methods experience some collapse, it's close to 100% for everyone. So which isn't particularly informative at this point. But the story is in the magnitude of collapse that is shown in the middle. VABL is like 38% collapse, MAPO 76% collapse, which means that VABL is twice as stable as than MAPO. So why does this matter, right? Like, what happens with this collapse, or like what happens if there is a large collapse? So in practice, think if you're deploying like a multi-agent system, you need to know that your agents won't suddenly forget how to work together. A method that reaches like peak performance and then collapses is actually dangerous when you deploy it in real life. You might deploy after seeing the peak. You're like, this method is working very well, and then you deploy it, only to find out that the system has degraded. And in the autonomous driving scenario, you can think of it like you deployed thinking that it's working well, and then it ends up in crashes and stuff. So VABL here gives you more reliable coordination through training. So as a researcher, it's not about like it works or it doesn't work. It's about why it works, right? And this ablation study is about why exactly does our model work? Like, what is the main thing that's working in our model? So we have a bunch of things that we have put together. So we want to like go through them and look at what's happening here. The full VABL here is with both attention and auxiliary loss. The first row here is the full model. It achieves the best reward of 100.5. That's our reference point. So now what happens when we remove the attention mechanism? Like, let's say we remove the attention mechanism, suddenly it collapses. From the best reward goes from 100 to 60. That's like a 40-point collapse. So this tells us that the attention is the primary driver. Like I emphasized throughout the presentation that this is the driver that looks at everything in the observation. So by removing that, there's like a huge collapse. So attention is critical to our model. So what about removing only the auxiliary loss? Like the third row is just removing the auxiliary loss. Interestingly, the peak performance is similar. It's 101.5, but the training dynamics change. The auxiliary loss contributes to more stable belief learning, even if its absence like doesn't crater the performance directly, but it will show up in like learning um, like what exactly to learn for the attention mechanism. And the fourth row here is shuffling teammates' actions. What we are doing here is we are breaking the causality. Uh, by that, what I mean is like the previous teammates' actions don't affect their current action. So uh, what this also suggests is like by breaking the causal pattern here, the the best performance drops from 100 to 85.5. What this means is that agents are trying to attend to random information and it degrades the performance. So the previous action and the current action are not related, but one of the main advantages of our model is that we look at all the previous actions as well, and that helps us predict what the current action is going to be for all our teammates. So by breaking that, it obviously like degrades the performance. And the next row here is like we're reducing the visibility to 50%. By reducing the visibility, it drops the peak performance down to 55. This makes sense because like the less you can observe, the less you can attend to, in the sense like there are like 4 agents and you can only look at one of them that or 2 of them because it's 50%. So that hinders our performance because we are not able to infer the other information from this. And the worst case, we are removing both attention and the auxiliary loss. The final reward drops to 9.1. This is the lowest in the table. Both components matter and they're complementary. So the bottom line is clear. So the attention is the primary mechanism that's driving VABL. The auxiliary loss is providing complementary regularization. Together, they produce the best results. So let me take a step back and give you more intuition on why all of this works. On the left side, uh, it connects it back to the work of cognitive science, the theory of mind, um, the ability to attribute mental states of others. What this is doing is like it's the cornerstone for human social cognition, right? Like because it is how you know that your colleague is about to ask you for help before they say anything. So they walk up to you and you look at them and you're like, okay, he needs some help. You observe their behavior, you attend to their relevant cues, you infer their intention, and you anticipate them, right? Uh, so that's what is happening here. You observe them, you attend, you infer, and then you anticipate. So VABL implements this in a computational version. So it's observing teammates' actions, attending to the relevant teammates, inferring what the likely strategy is through the belief state, and anticipate what they'll do next through the auxiliary prediction. On the right side, why the greater stability? There are 3 factors. The first one is that the GRU maintains smooth belief evolution. That means there is a belief state that is being updated after every observation. They evolve gradually, and that is why it prevents the sudden strategy shifts that causes the kind of collapse in MAPO, right? So because we are updating this with uh, like only 20% of it every single time. So like let's say there's one bad actor, there's like one event that happens that doesn't like completely push your belief into like making wrong predictions. The second is attention selectivity. Like the agents are focusing on the relevant teammates, they're reducing noise. So by focusing what's important or who is important in a particular observation, the attention selectivity selects only the ones that provide most relevant information for us to take the decision. And the third, the prediction task anchors, like the prediction uh, regularization, it anchors the beliefs to reality. The auxiliary loss prevents belief drift. If belief starts encoding irrelevant information, the prediction accuracy drops. And this, like once this accuracy drops, it tells the model like you're going in the wrong direction. You have to pull your gradients back. Yeah. And this is for whoever wants to replicate our work. There's a practical note on what it took us to get it to work. So there are four techniques that turned out to be essential. First one is the value normalization. It's a pop art style normalization, meaning that if there are like different ranges for all of these values, it will still work on that. For example, 0 to 1 versus like 1000 to 2000, like if there are two different ranges, the pop art style still works on that. Um, and the orthogonal initialization, it improves the gradient flow through the deep network, leading to more consistent training dynamics. And we use a constant lambda of 0.05. We tried like annealing schedules, setting it to a very high value first and then decaying it down to 0. Uh, but with other stabilizers in place, this had very limited effect. So a constant value works just fine. So like for deep learning from a deep learning perspective, it is one less thing to tune. And importantly, we match the Mapos configuration for like a fair comparison. Uh, the PPO epochs are like 10. This is matching the Mapos configuration, and the same clip normalization, 0.2, and entropy coefficient of 0.01, and GAE of lambda of 0.95. Yeah. So hyperparameter sensitivity. So I told you that we did the schedule annealing and we went from like a very high value down to 0. So uh, let's look at why we decided to set it at 0.05. So at 0, you have no auxiliary learning. Uh, what it means is that the auxiliary uh, loss had no impact on the belief system. At 0.01, there's a small benefit. The auxiliary loss is there, but it's barely contributing. The sweet spot here is 0.05. It provides enough signal to shape the beliefs without overwhelming the task objective. The task, so like at 0.05, it is helping the agent learn good coordination. At the same time, it is not overly relying on that. As you start increasing it further to 0.1, it is still good, but it's slightly more worse than 0.05. But it is in the same ballpark. Uh, but when you go higher, when it goes to 0.5, the performance degrades by a lot. So the auxiliary loss starts to dominate, and it starts pulling the network's capabilities away from the actual coordination tasks. It becomes more about predicting the other agents' actions rather than building good coordination between agents. And at 1, it's poor. So it's just too much weight, and you're just focusing on predicting other agents' actions. So the encouraging takeaway here is that lambda is not a sensitive hyperparameter, so you don't need to tune it to like 3 decimal points. Anything from like 0.01 to 0.1, it gives you very reasonable performance. So that suggests the method is very robust. So summarizing the contributions, first, VABL framework itself, it's a very novel approach to multi-agent coordination. It uses attention-based belief learning to enable implicit coordination without any explicit communication. The second, the stability advantage, VABL is twice as stable as MAPO with a 38% collapse versus 76%. So the belief mechanism provides smooth coordination that that resists the catastrophic forgetting. The third mechanism insights from our ablation study is that attention is the primary driver with a 40% peak reduction when it is removed. The auxiliary loss just provides the complementary regularization. Fourth, the practical impact. This approach is directly applicable to the autonomous driving, robotic teams, and any settings where they require any setting that requires coordination and has very limited communication bandwidth. And I want to be transparent about what we haven't done yet. On the limitation side, we have tested on cooperative benchmarks, overcooked and simple environment. But the multi-agent reinforcement learning community also looks at like StarCraft micromanagement tasks. So this is one of the other benchmarks that we are working on currently. We haven't compared it against like the communication-based methods like ComNet and Tarmac, or these comparisons would clarify or strengthen our case further on like where VABL sits in the broader landscape. On the future direction side, scaling it to SMAC, it's the StarCraft and Google Research football. So these are some of the other tasks that we want to work on, and we also want to work on like the theoretical bounds on how far theoretically can this model go. And what I'm most excited about is applying this to autonomous driving coordination, which I'll talk about next. So this is where I see the long-term impact of this work. So the VABL's belief-driven coordination, it maps naturally to autonomous driving. Think about these four scenarios. Intersection negotiation, vehicles arriving at an intersection and then needing to decide who needs to go first. So with VABL, each vehicle can infer the turn-taking intention of others and their observed trajectories. No V2V is required at this point. Highway merging, a vehicle approaching a merge zone, it needs to find a gap. VABL would let the merging vehicle build beliefs about where the nearby vehicles are. Are they maintaining gap, or are they are they still maintaining the lane by driving through? And the third one is platoon formation. So this is where the trucks are coordinating based on like speed and follow distance. The belief mechanism enables anticipation of like leader behavior, allowing for smoother and more fuel efficient formations. And the fourth one is emergency response. First responder vehicles, they are coordinating on routing and resource allocation when the communication infrastructure might be damaged. The common thread here is partial observability and limited communication, exactly what the conditions VABL is designed for. And remember that VABL executes using only the local observations. So deployment doesn't require any more infrastructure. It's just your agent and with the VABL architecture in it. So thank you for your time. I really enjoyed sharing this work with you guys. So at this point, I guess I'm happy to take questions, or if Avinash wants to take over.
Yeah. Thank you, Vishnu. Thank you for sharing your research. The floor is open for questions. I think I saw
May
Dr. Iman Kamarian's. Yeah.
yeah, may I go first?
Yeah, sure. Okay.
Yeah, because I
After
have to
this,
go.
we can get back to Dr. Iman's question. Yeah.
Yeah, I have to go for some other event. Yeah, very nice presentation. Thank you for the presentation, Vishnu, and hope for the best for your future endeavors.
Thank you.
Just a few thoughts, like just because these are not something to do with directly with your research, but I was just curious for future somebody else can take some pathway taking from your research. So because our this SRL group is very familiar with satisfying approach, and I try to keep exploring application of satisfying against optimization. Recently, I had seen one paper from Takahashi et al. I don't know whether you are exposed to that, but there are efforts for applying satisfying approach. Satisfying is just, if you're not familiar, something which is an alternative to optimization. Because as Farooq says, optimization is oxymoron in certain conditions. So where satisfying is more appropriate and optimization cannot be done. And Takahashi's paper actually was one of the pioneering papers applying satisfying approach for reinforcement learning. So I was wondering that I'm sure that somewhere you used the word belief. Belief is inherently something which is cannot be a specific optimization of belief. It's impossible, right? So belief and theory of mind or something like that. You used certain terms. I'm not fully conversant with those terms, but I was just wondering whether you have thought of any possibilities of applying this satisfying approach in your reinforcement learning models. Thank you.
Thank you. That's a very elaborative question, and it's like I would certainly want to sort of like look at these methods and try and incorporate them. So currently, the focus that we were working with has been on trying to develop the trying to develop like predictions based off of the current observation and like teammates' actions, right? So in our case, like if I were to take like a satisfying like the approach that you were talking about, then I would sort of introduce more like this is how I'm thinking about it, is that I've been implementing more constraints. For example, if there are like 3 agents, it would be 3 constraints that I have to satisfy. And if there's like more than 10 agents, then there's like more than 10 constraints I want to satisfy. The whole machine learning field, I can say, is more about like approximating these things rather than like getting the exact solution, I guess. And that is where the term, I guess, belief or optimization comes in for this field particularly. But yeah, I would definitely want to explore. If I can like get my hands on that paper, I'll definitely read. Like, I'll reach out to you to like sort of get that paper
Yeah.
and go through
Yeah,
it.
thank you very much. I will let others answer, ask more questions, and I will
Yeah.
share the link for the paper which I'm mentioning in the chat. Thank you.
Perfect. Thank you so much.
We also have Dr. Atik Zaman, Vishnu's advisor. If he would like to add some value, please go ahead.
Vishnu is doing a great work.
Thank you.
I think he's doing fantastic. Thanks.
Yeah. Thank you. Dr. Iman, you had a question.
Sure.
Please go ahead.
So please go to the slide that you talked about, the loss function. So there, my question, so if you go to that place, so when you talk about variational, it looks to me that you are trying to maximize the evidence lower bound. Is it correct? So
Yeah.
the point here is evidence lower bound has 2 parts. One is maximization of the likelihood. The other part is regularization. When you use PPO, it makes sense to me that you say that, okay, I want to maximize, but still I want to cut it. If it goes too much, I want to cut it to be loyal to the behavior policy that previously I had. So I do not go very far from it. So this is the advancement from TRPO paper. That completely makes sense to me. But the point here is when you use PPO, you only have the behavior policy, which is not well trained. And you want to use this for autonomous vehicle. So there you should have expert data. Means PPO is for online on policy. But bringing a model, a policy model, which is not well trained to roads and do autonomous vehicle is really dangerous. So you should switch to offline policy, offline training for doing the job. So the point here is you formulate the problem by PPO, which is for online, but the problem that you want to solve must be done in offline. So that's a little bit confusing to me, that how you trust a behavior policy which is not well trained instead of using expert data. And then if you do that, then how do you calculate this elbow? Means how do you do the regularization and those type of things? So I'm thankful if you answer this.
Yeah, that's a great question. So like the offline approach would be like training the whole model on the data that we have, and then we would then put it onto like, let's say, autonomous vehicles, and then we let it do its job, right? So the like shrinking down the question, what I can like just summarizing it is that like in this training objective, what is happening is that it is updating its belief as it's going. And then like this would be very dangerous in autonomous driving scenarios, is what Dr. Ian's been mentioning. So like think of it this way, that we are looking at like current scenarios, and we want this development to happen in those scenarios. So for example, so obviously there's like a lot of testing that we have to do in order to like go for like a complete deployment. But the idea here is that like when there are cases where these agents need to make decisions. Like currently, they are limited with what they know, right? Like, for example, the autonomous driving cars right now, they have a hard time either merging or like keeping the lane, for example. I mean, like changing the lanes and getting the optimal lane choice and these kind of things. These subtasks can be improved by using these training objectives, where if the maybe a good medium would be where the agents are not able to decide something, they can go ahead with the training objective that we have, where they are updating their belief for that particular subtask that they're performing.
Yeah,
So,
thanks for your response. But the point here is we cannot trust the behavior policy, which is not well trained. So if you formulate the problem in a way that you use expert data, then probably you can do better, because whatever we want to do, even super basic subjects, if you start in online training for on policy, then probably the first try will be the first crash of your car. So this is the point that I want to say.
yeah, thank you for the insight. Yeah, I'll make a note of it, and yeah, maybe like formulating the problem, we can like change that.
Also, why don't you try to do contrastive learning? So this type of cross attention that you do, maybe it works, but if you slightly go out of distribution, then I'm 100% confident that it will not work. So I want to see that. Why are you interested in formulating the reward and then use this approach? Why don't you switch to something like energy-based models and then formulate your reward based on the probability? So you can simply formulate the reward as a probability of reaching to the goal given the state action that you have. So this way, you completely ignore the reward system, the reward engineering of the problem that you want to do. And also in energy-based model, similar to the idea of clip model, you can have two encoders similar to what you have here, but you project to the joint space and then calculate the distance. So if you have some trajectories for expert, then you can say, okay, this is the state action that I have, and this is the goal that I want to reach. Minimize the distance. Then for any random goal that you choose from marginal distribution, you can do the negative sampling. And then a simple inference can help you to train your model. So this can be maybe some suggestion. Okay, thank you so much. I enjoyed
Yeah. Thank you
hearing
so much.
about
Great
your
one. Yeah,
presentation.
those are good
Thanks.
suggestions. Yeah, thank you.
Thank you, Dr. Iman. Does anyone have any other questions? Dr. Janet Allen, if you would like to add something.
I appreciated the presentation. I have been working with some other people on trying to understand how things coordinate, and I would like to see more of this and perhaps incorporate it into what we are doing.
All right. Yeah, I'd be happy to like help if I can in any
Thank
capacity.
you.
Yeah.
Thank you.
Thank you, Dr. Allen. Does anyone have any other questions or comments? Roshan?
I mean, the question put was interesting and how you approached it. I think I'm trying to like sort of understand how this can be helpful in like engineering questions specifically. So like our research is more materials based research. So maybe belief is not necessarily a problem there because either it is possible or it's not possible, right? So it's like a black and white, yes or a no kind of a thing. But still, it is interesting because I've heard about a lot of autonomous vehicles and how they sort of behave, but this is an interesting perspective of like being in certain situations where you might not necessarily have abundant training data because nobody will tell you what is the right thing to do when, as you said, there are no constraints on like stopping or anything, but you have to observe and make a decision. So I think that's something that I'd never thought of as a perspective of like, oh, this is how somebody can think about that problem. So something new for me. Thanks, Vishnu.
Yeah. Like your first question about or the question about how you'd like sort of have them in the engineering side of things is like I would think of them more like I know you guys, so it's more about like the experiments that you do.
Yeah.
So it could be more of like a coordination a task kind of thing where you know how much time you want to keep and you keep adjusting based on what things you're doing.
Right.
In the sense like how much time you want to do a certain what do you say a task, like for example building your epoxy things. Um, so what can happen is that based as you go with time, it learns what needs to be done for a particular uh, material
Right.
and how
I
much time.
mean, the problem that I mean, I'll put this to you in a way like, so what generally people are trying to do is that people are trying to do, so what we try to do is like we try to simulate material families, so like a family of certain material systems, and computation can be easy or difficult based on how symmetric or asymmetric the crystal structure is.
Mhm.
But essentially, the idea eventually what we want to do is that without doing any simulation, based on the data of the family of trained materials where we have simulated data and we sort of tell it, so this is the crystal structure, these are the atomic parameters, and this is how the final observables look like.
Mhm.
Based on this, if I give the model a structure, would it be able to predict the values without me having to do any kind of simulation? So like that is one direction that we are sort of like looking at, is can we train the model to give me those interatomic interactions based on previous things where it is able to predict without me having to run it through any solver essentially. So through my data, it understands the physics, and based on that, can it make a prediction of the final properties? So that's what we're sort of trying to achieve.
I see.
I would be interested to know your thoughts on like how one could do that, you know?
Yeah, and for those kind of tasks, I think this model is not the right fit there.
Right,
But I would go with something more like an unsupervised learning approach, like a machine learning
right,
approach, where you cluster all the previous results that you have,
okay,
and then with a new element or a new material that you're testing, you can give the parameters that you have, and it
yeah,
will sort of put it in a ballpark, like saying that it belongs to this cluster. I
right,
guess
exactly.
that's the right approach there.
Thanks, Vishnu.
Yeah. Thank you, Roshan.
Yeah. Thank you, Roshan. Any other questions from the audience? If not, then
I have a
Farooq,
comment.
if you, yeah, sure.
I think in different ways, we are all looking at the problem of coordination, cooperation. And in essence, what we are looking at is how do we give intelligence, computational intelligence to machines? That's what we are talking about. And then how do the machines coordinate this information to do something of value? And I think there's a philosophical foundation for this. A lot of what I see happening here is people approaching it from the mathematical side. I'm interested in understanding it from the philosophical side. And you've touched upon it today. You talked about cognition, you talked about that. And so, in that sense, I'm extremely pleased at being part of this conversation because here I see people not saying, how do I solve this problem? How do I play this game? How do I do such and such, but saying, what is the
cognition that you want to represent computationally? How do you represent a human being computationally? And this is what excites me about what was presented today.
Thank you so much, Dr.
Vishnu, any comment? Atik, any comment? Roshan, any comment?
I think I have something to say here. Like when I started working on this, that is exactly how my thought process went. I think I started looking at it in a very philosophical manner, and then I had to get the mathematical constraints and like try and fit it into like a computational or a mathematical structure for the I guess for the machine to learn. But in essence, what I started with was like, can machine do this? Like, can it, so autonomous driving, can it go through the unsignalized intersection without having to like wait for someone else to tell it what to do? Like, yeah. So yeah, I think you've summarized that very well for me.
So
Thank
I'm
you.
interested, Vishnu, in understanding the philosophical or the cognitive underpinnings of what you're doing.
Mhm.
I'm less interested in the mathematics.
Yeah.
And I think if you want to talk about this stuff sometime, let's have lunch. The four of us can have lunch, chat.
Yeah, we'll go
Just
for
have a
lunch.
good time.
Yeah, we'll go for lunch sometime. I mean, when Vishnu started working with me, I work on connected vehicles. So I told Vishnu that here is a problem or application which can be used in your work. So he took this unsignaled intersection and put in the communication stuff. So that's how we're progressing.
Great. Karishma is in the United Kingdom. I don't know when she joined us. Karishma, do you have anything to add? Okay, thank you.
Thank you.
Yeah. Yeah, now the floor is open for chit chat if there are no
So let me
questions
stop.
then. Yeah.